All right, so my name is JF. I work on Chrome for Google. And today I'm going to talk about C++ on the web, Ponies for developers without pwn'ing users. I have given a talk with exactly the same title in abstract somewhere else. This talk is entirely different, just to confuse people. So today I'm going to talk about putting C++ in browsers and arbitrary C++ that you may create that will run inside the browser. That sounds like a completely mad idea. You've probably all heard about NPAPI, ActiveX, and a bunch of other things. You've heard about Java getting owned all the time. And so putting C++ in a browser sounds equally silly. So C++ in your browser, it's more likely than you think. And actually, as you probably saw last year at CppCon, Alon gave a demonstration of mscripton, and exactly this is possible today. Right? So what I'm going to talk about today is three things. First, I'm going to demo a few things that are possible today. Right? So I have a Chromebook here. It's a wonderful Chromebook Pixel 2. It's very secure, and I'm going to run cool things inside of it. I'm not going to focus on games because Alon did that last year. I'm going to focus on other things. So today I want to convince you that C++ on the web is a thing and you want it. Right? So I'm not talking about writing a browser in C++. I'm talking about developers running code inside the browser on anyone else's machine. And then I want to convince you that it's not a totally bad idea for security. Right? So you went to a few other talks this year, I assume, that talked about security. And by now, you already know that undefined behavior is very complicated in C++. And so you're going to think as soon as you have one wild pointer, anything could happen to the user's machine. That's not quite true. I want to convince you that that's actually the case, and that you should actually continue using Chrome or Firefox or IE or Safari or whatever browser you use. And then I kind of want to go under the hood and showcase how security actually works. Right? And there are two goals here. Really, again, it's to convince you that we're not completely silly, but it's also that some of it is usable by you, right? Remember, a browser is just an application, and so there are things that you could use from what browsers do that may be useful for application security in general, right? And I'll dive into that a bit more today. Now, of course, I work for Google. I'm going to talk about Chrome. Partly because I can't competently talk about what other browsers do, because I don't work there, I don't know what they do. It's open source, I can go look, I talk to them pretty frequently, but I wouldn't represent what they do very well. Now, what I'm going to talk about, other browsers also do, right? They're not completely silly, we do collaborate on many things, right? And in the same way, I'm going to talk mostly about LLVM when I talk about toolchains, because that's what I work on. I'm sure MSVC does wonderful things. There were presentations about that this week. And I'm sure GCC also does wonderful things, right? I just don't work on these, so I can't really competently talk about that. And a lot of what I'm going to speak about is not my work, right? I work in a pretty big team. Chrome security is pretty big. And we do a lot of great things. And we interact with other teams within Google, right? So you've seen Kostias talk about sanitizers yesterday. We work pretty closely with Kostya. So not everything in this in my work, and I'll try to point it out when I talk about it. So I'm going to start off with a nice little demo, right? So I'm going to just start off showing little ponies that we have, cool things. Again, this is just a Chromebook, right? So I have this little thing here. This is just a web page, right? And I'm just going to press this, and I'm going to run this, right? And so this looks a bit silly. Okay, it's Bash, but anyone can write some JavaScript and print out Bash to a black screen, and okay, trust me or not, this is Bash. So I can obviously just run ls. So I can't really emphasize how this is actually Bash running. This is actually ls running. We took the source code from GNU, and I'm running this inside a browser right now. And again, it sounds pretty simplistic, right? Like, cool story. You have ls running inside a browser. That's great. So, I can just go and create random files, and that works. And, I have times and other stuff, and that's kind of cool. Again, I can, echo or something like that. And I can just go and cat things out, right? So I just read a file. And that's kind of interesting, right? Now, that's not super complicated, right? It's a few programs, there's a few syscalls, it's probably trivial to emulate, right? So let's do something a bit more complicated. I can kind of, start different applications, and I can, kind of go and do stuff, and that's kind of cool. But I can do things that are a bit more complicated, right? Date time is actually quite complicated. If I can type. Right, so again, this looks a bit simple, but what actually happened is that within the browser, I have a whole sandbox, actually multiple layers of sandboxing that I'm using. And what this did is this asked the operating system, what time is it, right? Now, just to illustrate how complex this is, you can't just ask the operating system anything, right? So when I have files in there, I can't just go and create files on the hard drive willy-nilly or just read any random file, right? Especially right now I'm running from localhost, I couldn't go and read from google.com or yahoo.com or facebook.com and do whatever I want, right? So there's a whole layer of security around being able to do these types of things, right? And in effect, the browser is presenting itself as an operating system to the application that I compiled, right? So it's this kind of special operating system that happens to present itself basically like any POSIX application. If I go, there's this little kind of nice extension that exists that I can see and kind of browse, right? So it's actually an operating system that's in there, a little file system that's inside the browser that I can just kind of go around. And so I can do a lot of interesting things with this. So I just did a control D inside of Python, and that seems kind of silly again, but Python is actually running inside its own process, right? So what I'm doing right now is I'm forking a bunch of processes as I type anything, right? And again, that sounds pretty silly, but if you go back to original web in JavaScript, it used to be that everything was in one process, and everything was running inside an interpreter, right? So that means I can fork different processes, do a bunch of interesting things. I could try to fork by my machine if I wanted to, or if I were malicious, I could do really bad things to your machine, right? So I'm going to try to convince you that that's not doable. Now, running Python is pretty simple. It does print to the screen. How does that work? We do pretty silly things in this demo. For example, I'm using JavaScript as a microkernel, which sounds completely ridiculous until you realize that JavaScript is based around post message, right? So what this means is that it's an asynchronous kind of programming model. And the way one part of the browser talks to the other one is through a message loop. And all you're doing is just doing post message, which is effectively equivalent to pipes inside of a kernel, right? So JavaScript is the little microkernel that starts different tasks and that makes sure that they can have pipes that can communicate to each other. So that's kind of interesting. Okay. Yeah, so let's go and go here. So in there, I have a .cc file, which is kind of cool. And let's just go and run Emacs on this. Now, wait with me for a minute. I am actually running Emacs, right? So I have to start Emacs, which is hilarious. Now, I use Emacs every day. It's much faster than this to start. Why does it take so long right now? Well, it happens that doing portability is actually quite hard. In this case, Emacs, it takes quite a while to start evaluating all your eLisp files and do all my pretty color highlighting. This is actually the color highlighting I use at work. And usually what Emacs does to make that faster is the first time it starts up, it parses everything, and then it segfaults itself, and then loads that again next time, right? So that's really cool. We don't have that working right now. I'm sorry. But Emacs actually works, so that's kind of nice, right? And for all the other people in the room, I could go and just kind of start up the makefile in Vim. Right, obviously, now that was super slow. You noticed, right? And so yeah, Vim also works, of course. And the one useful command for Vim, it's cool and cute. Come on. So yeah, you can do kind of interesting stuff, but obviously, okay, that's cool. You have a makefile and a .cc file, and you're just kind of browsing through them. That's cool. So let's do something a bit more interesting. I'm just going to make -4, and I'm going to run LVM inside of this. So of course, make .j4 it forks multiple processes, and it's just building this little demo that I have here. Now it is, I configured it so that it prints out actually what it's doing. And then I have this output here. And so I created new files. And I can just kind of run the hello program. Sorry, where did I put hello? Oh, yeah, sorry. So it's a portable executable, not just a regular executable. It says hello world. And then I have a separate little demo in this folder, which uses GL. Now, it's not the prettiest demo ever, but it creates what kind of looks like fire by talking to the GPU, which is kind of cool. And as you saw last year, you can also just kind of create games out of that. Right? And it's not as great as it could be. Right now, it only supports GLES 2. Pretty soon, Firefox as well as Chrome are going to support GLES 3. If you care about games, that's probably something that's really good for you. If you don't care about games, it's going to be prettier. So whatever. So okay, that's kind of interesting. You can do kind of cool stuff. And then, just for brevity, I'm just going to go to this folder here where I have a little Fibonacci thing. And I was lazy, so I already pre-typed my build command. I'm just going to run this. Right, so I get a warning. That's fine. I don't care. And then what I did here, if ever you work with LLVM or LLVM's internals, I created two files. I created a .l file, which is a bitcode file for my little Fibonacci program, which I probably should have shown you. So let's let Emacs start. And so what I'm trying to show here is I can do the whole kind of thing that I usually do with LLVM, right? So as a LLVM developer, I often kind of end up creating .l files, and this one looks very pretty. It's been optimized, right? So it's a beautiful Fibonacci program. And then I also created a JavaScript file here because I can, right? So I do work on Chrome. I do work on Portable Native Client, but this is a JavaScript file. It's ASM.js code. And so I'm running LLVM as well as Pinnacle as well as ASM.js inside my browser. And so I could take this and pipe it to JavaScript if I were so motivated, which I'm not, and I could execute it, right? So I'm showing you how I can run different things using different tool chains inside of my little demo here, which is kind of nice. So the other thing that I'd like to show you is that this isn't actually only something that can run applications. I can also go to, say, GitHub. I wrote a bunch of cute papers for the C++ standards committee. So I'm just going to go here and copy this URL. And then I'm just going to clone my repository here. And yeah, so I'm talking to GitHub right now, cloning a repository. And then here's my paper. Right, so I have a whole Git thing. I can show the Git log here if I wanted to. Or not, but whatever. Oh yeah. Right, so it's beautiful. Right, so we have nice little papers and everything. So again, it seems pretty simple, but like having all these things just working kind of shows you that you can do complicated stuff. And if you know the internals of Git, it's beautiful, and that's written in very kind of tight C code and Perl. And when you do things like that, it just kind of runs all these things left and right and does very complicated stuff, which like I don't have to care about because someone else built it for me and just works. So yeah, that's kind of cool. And at the same time, this entire demo I've been running from Python's simple HTTP server here that's running inside another window. So I'm just serving from localhost, which is also running inside of a sandbox, right? So obviously, you don't want any web page to be able to create a server locally, right? So this is actually running as an application inside of Chrome, not as a web page. But it's using exactly the same technology with extra permissions. So when you install that application, it says, hey, I'd like to be able to start a server on localhost, and you can say yes or no, right? That's kind of interesting. So and if I did this here and I did that again, I think it would say, oh, it's cached, but it would say it's sad if I reloaded it or something like that. It'd be like, oh, I can't talk to the server. Yes, leave the page, and it's like, oh no, I can't talk to the server because I killed the server. So that's the extent of my demo. So my goal today is to kind of convince you that we can do interesting stuff inside of a browser, right? And I think that's kind of a showcase of what we can do. Again, we can do a bunch of other games, and it's a thing. You may want to use it or not. But what's interesting is C++ has a bunch of code that already exists, right? And I'm not a JavaScript hater. JavaScript is actually quite nice for some things. But I don't want to use it for high-performance applications, for games, or anything like that, because I actually care about battery life. Even though I have a Pixel, which has a very long battery life, I don't want to do everything in JavaScript, right? So the other thing is it's just a nice language to use for certain things, right? And what I'm trying to demonstrate here doesn't just support C++. I've heard a lot of mentions of Rust, right? Bjarne mentioned it yesterday, so did Herb. It should also be able to support Rust as well as Go, as well as Haskell, and anything else, right? So any language should work in this environment, right? It's a bit silly that I can only target the web with one language. I'd like it to be this kind of nice thing that just works with everything very well. So it is a conference about C++. I'll try to concentrate on that. But yeah, what's weird today, if you've tried to use what I showed you, is not all of the solutions for running C++ on the web really allow you to use all the features of your machine. Right? So if you've used mscripton for now, it doesn't quite support threads. It doesn't support SIMD or other stuff like that. If you've used portable native client, well, it does support threads. It supports 4 wide SIMD, right? So 128-bit wide SIMD, but it only works in Chrome. That's kind of a pain in the ass. And there's this kind of whole evolution of different browser vendors trying out different things, right? So that's kind of a problem, and it'd be great if everyone kind of worked together to create one thing that you can all use and not have to figure out different tool chains, different capabilities that you can use and whatever. And this is actually exactly what we're doing right now. So if go back to the internets here, we've been working for a while with Mozilla, with Microsoft, as well as Apple, on a thing called WebAssembly. And we have this beautiful design. And right now, it's basically about a design, nothing else. But we have a few implementations and stuff like that. But the goal is really to be able to do what I showed you portably in all browsers, and not just do like, oh, OK, let's run single-threaded code and like not be able to handle signals and not be able to do GC and all these other things. The goal is to actually do everything that you can do in a C++ application or any other language natively and very efficiently. Right? So that's what we're trying to build towards. Now, right now, this is all hot air. There are a few demos that you can go and play with. We have like a whole repository, but none of it is like actually usable inside a browser today. It kind of is, but you have to kind of get your feet wet. So I don't recommend trying it out today, but it's coming like fairly soon, right? And the goal that we have is to build something evolutionarily that that will have all these features. Now, again, it's pretty critical that security kind of be there. Right? So we don't want to compromise on security just for the sake of giving you cool features, right? So how does it work in general? If you're not familiar with the current tool chains, well, basically, on your machine, you're going to have your source code, and you're going to translate that to an executable, right? So if you use portable native client, or if you use mscripton, you're using a close to tip of tree fork of LLVM. And you do that translation, right? So in portable native client, you create a PXE file. In mscripton, you create a .js file. And what you then do is you upload that to the internets. And then on the user's machine, the user downloads that and executes it inside their browser. All right, of course, they use Chrome, but that's my example, so I get to put Chrome there. Now, what's interesting to see here is that the C++ code is all linked into one final executable right then and there. Right? So a lot of the optimizations that you would do if you were running on your machine happen right there on your machine. And the only thing that the user's machine needs to do is it needs to say, hey, I have this executable that you told me was portable. All I need to do is execute it on my machine. So if the user's machine is x86, it needs to compile that kind of portable intermediate format to x86. But that's about what it needs to do. If it's ARM, it needs to do the same thing. But that means if you work on compilers, you're doing instruction selection, register allocation. That's about it, right? So it's not that much work that you need to do. You only need a very small and nimble compiler to do that. Whereas if you're compiling something like JavaScript, well, JavaScript's this big and heavy thing that needs to do a bunch of things to be fast, right? So we've run most of the optimizations on your machine, so the user doesn't have to run them. Right? And keep in mind that browsers reach a few billion people. Right? I think Chrome's install base is like getting close to 2 billion right now. So on your machine once and on up to 2 billion users' machine many times. Right? So you don't have to run the same optimizer back and back and back. So that's kind of interesting. And the goal is for it to be very similar to cross-compiling. Right? So if you install Linux or something like that, you download the pre-built Linux image from the internet, and that's pretty often been pre-compiled, right? So it's just cross-compilation to a different architecture. It's not that hard, right? So the fundamental technology, how you would use it as a developer, is pretty much the same as developing things for a native environment, right? It's the same as like if you're an Xbox developer and you target the Xbox, you're going to use a special toolchain, but it mostly kind of works. Some of the APIs are a bit different, but yeah, it's kind of the same thing. So one thing I kind of want to clarify is I've been talking about security, and I kind of want to drive home the point that browser vendors have a different idea of security than a developer has in this context. So in general, as browser vendors, we mostly fight for the user. This is Tron. I can't use images of actual Tron, so this is Tron guy. But we mostly just fight for the user, right? Like you as developers don't really care about the user's security. Like you're not trying to hack them with your code, right? You're all honest people, right? So the problem we have as browser vendors is we can't trust all of you, right? Like sometimes you just screw up, or sometimes you are actually malicious and you're trying to hack into our users. And so we have to defend the users and really kind of build a platform that works for them. So that doesn't mean that security of your application is something that we give up for the sake of the user's security, right? But when I talk about security, I'm talking mostly about what we've done inside of Chrome to make the machine secure. You can do a lot of the same things inside your own applications, running inside of our sandbox, running on the user's machine, right? So if you're, say, a bank, and you're running code inside of a browser, there are certain things that you have to do for security, right? You don't want your banking code to be running on the user's machine and like get cross-site scripted or something like that, right? So that's a thing that you have to think about as well. So that kind of brings us to a critical point. Whenever you do anything related to security, so we have a security team within Chrome, and basically we have a questionnaire whenever we want to launch anything, and they ask us, so what's your attack surface, right? And you should be asking yourself the same question if you care about security. What's the attack surface? Now, in our case, the answer is kind of scary. There's nasty stuff on the internet, right? And that's our attack surface, right? So that means that like we're going to run any web page, just anything, right? And that's a bit scary, right? Most applications that you may be developing probably don't have such a big attack surface unless you're writing, unless you're writing something that's facing the internet and then you're just serving a bit of data and you're allowing any random input, right? But SQL injection is a thing that's been discussed quite a bit. It's still a thing, but it's much easier to secure yourself from SQL injection than it is to secure yourself from everything, from running arbitrary C++ code. And so what's interesting also is we ship browsers to the users, but we don't have a clue as to what the browsers do afterwards, right? Like you download a browser on your machine, and then that's it. Yep.
You want to enable cross-site scripting for C++?
So we don't want to enable cross-site scripting for C++. Basically, a lot of what we do reuses the same APIs as the rest of the web platform. Now, in some cases, because it's a new platform that we're developing, right, this kind of WebAssembly virtual machine, we can actually narrow some of the mistakes that were made by the web in the past. So we can offer the same APIs with extra restrictions, but in general, the rules for how you build something securely will be the rest as the rules for the rest of, for other web applications, right? So if you're used to developing JavaScript applications, it's the same kind of security that you as a developer have to apply to your web application. If you're not used to it, there are a bunch of books about it. Yep.
For the portable assembly, is this also dependent on like some of the new features, like the networking features that are built into, or that may be built into C++ 17 or beyond?
Yeah, so the question is are the features in WebAssembly related to new features that may be in C++ in the future, like networking or stuff like that? So that's a quality of implementation problem. And so the reason I say that is the networking APIs, for example, that are potentially going to be standardized in C++ are basically just implemented or implementable as using POSIX primitives, right? And so you saw earlier I was running Python simple HTTP server. If you install as an app and it makes sense to be able to reach out on the web and do things, then presumably you can use exactly the same basic APIs to do the same thing. Now, on the web, like I don't want you to be able to just go and talk to any server you want, right? So for example, in the case of networking, it may be that like there's going to be a little pop-up that says, hey, this guy wants to talk to someone else on the internet. Now, for most users, they don't know what this means. And so the reality is that it'll probably just not work, right? But there are different proposals on the web to add things like UDP support for games or for videos, video conferencing or stuff like that. So there may be things that are possible. But again, WebAssembly is just a virtual machine that runs things. The API surface will be basically the same as the rest of the web. Right? Okay. There may be shortcuts. For example, if you want to talk to the GPU, we could potentially make that more efficient. But talking to the networking stack is basically the same as just a JavaScript application talking to the network. Okay,
so basically if you wanted, let's say that you have like an interface where you're trying to load a bunch of numeric data, like, you know, for example, well, let's say that they're trying to compute a huge, like maybe a weather forecast in advance on their laptop based on weather information or, you know, conditions on the web. You're trying to develop that. You don't want to have the JavaScript, you know, overhead bloat, so you want to use the C++ to keep it fast and efficient.
Mm-hmm.
I kind of don't understand how that would be.
I'm sorry. Are you done your talk?
Yeah, so I'll go into that later.
Okay.
Right? Yeah. So sorry, but I'll go into that later. So basically, the attack surface that we have to care about as browser implementers to run C++ on the web is if you remember from the slide I had earlier, we take a portable executable and we translate it to native code. And so just that translation part, right, the compiler that takes the portable bit and optimizes it is an attack surface, right? And then the code that we generate from that is also an attack surface. So you know, the thing that takes the input can be attacked, the thing that generates can be attacked, and then sometimes we want to check that the code that's there is valid, so that can be attacked too, right? The validator that checks that that's correct is also potentially vulnerable. And then once you start doing calls, right, that's also vulnerable. All those APIs that we're talking about, especially talking to the GPU, is also something that's vulnerable, right? And I'll show some example of that happening in the past. So one thing that I want you to take out of this talk is really sanitizers. It sounds really basic. Actually, there's one thing that you should do before that. You should be writing tests. If you're not writing tests, go back and write tests. Afterwards, start writing the sanitizers. Make sure that like you exercise all of your code and that everything's correct. The paths that you execute don't reach into undefined behavior, and we do that, right? So as I was saying, our attack surface is the compiler, so we have a bunch of tests for the compiler's conformance, and we make sure that if we give it the inputs that we think are interesting, it doesn't crash, right? So we'll manually write tests that try to exercise really big numbers, really small numbers, really weird inputs, really kind of interesting inputs, and we'll make sure that we don't run into undefined behavior. Now, Kostya had a great talk about that. There are a bunch of sanitizers that exist to do a bunch of different things. So you can read up on them, but there's address sanitizer, thread sanitizer, there's memory sanitizer, data flow sanitizer, leak sanitizer, control flow integrity, and there's a bunch of other stuff, right? And you can also put assertions inside your code and a bunch of other things. But the main idea is you can run your tests and be told when your code's doing something really bad, right? And the problem with that is it has some amount of overhead. So you don't always want to do that in production. Maybe you want to run undefined behavior sanitizer in production. It's not that big of an overhead, but address sanitizer or thread sanitizer actually have a significant runtime overhead as well as a memory overhead. So you may not want to do that. So yeah, you're using C++ for speed. You know, you want to have your speed. Now we do that inside browsers to test everything that we do, but we write tests, we're not necessarily that creative, right? And so from very early on, browsers were doing fuzzing. So this comes from the original Chrome comic at the launch of Chrome in 2008. We were doing fuzzing back then, and so were a bunch of other browser vendors, right? So it's not like we're inventing anything, but fuzzing is actually quite hard, right? So writing a very directed test where you know exactly what's going to happen is it's pretty easy, but developers, myself included, aren't that creative, right? Attackers are very creative at finding the one weird input that'll break your machine. And so fuzzing is a way of crafting a code mutation, right? So if you know, for example, that you're parsing JavaScript as your input, then a fuzzer will try to mutate different types of input with the knowledge of how the JavaScript parser works or how part of the optimizer works, and try to mutate things. So it'll take inputs that you gave it, right? So you were not too creative, you created a few tests. It'll try to mutate it in interesting ways, and it's just a bunch of monkeys writing random code, and eventually something may crash. And that's where the sanitizers come in handy, right? Because you're trying to mutate the inputs, poke at your code, do interesting things, and sometimes they'll crash, and the sanitizers are great at catching that, right? So from very early on in the Chrome project, we were doing this, and it caught a huge number of bugs. Now, what's great is it usually catches those bugs before it reaches production, right? You check in your code, and then like, a few hours later or something, you get a report, and it's like, oh, hey, this thing crashed, and then you revert your patch, and then you fix it and push it back in again. Then you get reverted again because of some random other thing. But eventually, the code is statistically correct, right? So you've run tests where you thought, hey, I think this may break my code. Then some random monkeys came in and said, hey, I think this may break your code. And eventually, maybe it's correct. But that's not perfect, right? It's not a proof of correctness. And so after the monkeys, Kostia gave a great talk about AFL fuzz and libfuzzer. So the idea is you start to be a bit smarter about how fuzzing works. Right? So instead of just having monkeys that like intelligently try to mutate exactly this type of input or something like that, AFL fuzz and libfuzzer, they just kind of are more intelligent. They can create inputs out of nowhere without even knowing what your input looks like. So this little animation here was created by the author of AFL fuzz, and it took one JPEG image and it's playing with the format. This is like the actual fuzzer generating random images and trying things out, right? And so what it's doing is it instrumented the binary for libjpeg in this case, if I remember, and it looked at where all the branches were, right? And it's trying to figure out, hey, well, if I change this input here, the branch goes that way. If I change this input there, the branch goes that way. So it tries to exercise a bunch of different code paths inside of your parser in this case, and it has very little configuration. You gave it one image file, and then look at what it's doing, right? It's doing a bunch of random things that, like, if I were trying to test a JPEG decoder, I don't know how a JPEG decoder works, right? But this fuzzer is actually pretty good at doing it, right? It gets great coverage, and if you go to AFL Fuzz's webpage, they have a list of projects that, like, they found bugs in through doing this approach, right? And a lot of it is just like, you unleash it on this thing, and then it works. It's actually quite straightforward to do. So I highly recommend trying AFL fuzz as well as libfuzzer. They're slightly different to configure, but you don't have to craft this like really intelligent parser that, like, basically a reverse parser that generates inputs because you know exactly what will tickle your code exactly right. And we run that extensively on our bots for Chrome, and it finds a huge amount of bugs, even more than the handwritten fuzzers that we had before. It doesn't mean that the handwritten fuzzers are bad. They're just really hard to write. They're very custom, and this just kind of works out of nowhere. So that's actually pretty great. So those are kind of sanitizers and fuzzers are things that we use in production. But again, a browser does a bunch of things to keep you secure that you may want to use in your applications. Now, of course, it depends on what you're doing. But in general, I'll concentrate on tools. Obviously, if you do code review, that's cool because one person may introduce bugs without realizing. You should be doing code reviews. But you may want to use like libraries that check integer ranges or things like that. In general, I'll concentrate on tools that you can use instead. So one thing that browsers have done for quite a while that works really well is address space layout randomization, right? So attackers really like knowing where things are in memory. And I'll explain why a bit later, but if you don't enable address space layout randomization or stack cookies or stuff like that, you really should. If you look in the news a few days ago, there was an antivirus company that got owned by some developer at Google because they don't enable stack cookies, and that's really, really bad. Right? Like the antivirus just looks at a zip file, tries to see if there's a virus in it. The zip file is the virus, and then the antivirus gets owned, and the whole machine gets owned. That's really bad. Right, so compilers have really basic things, and operating systems have very basic capabilities like ASLR that you can just enable for your application. You should do that, right? It's really basic. Now, not all operating systems have great address space layout randomization because they kind of predate the research on that being done really well. So if you run on Windows XP, well, you're kind of not getting much entropy out of that. There are tricks around it, right? So you can go spelunking in the Chrome code base to try to see how we do that. Firefox is the same thing. Now, one thing that Chrome did really well when it came out that other browsers are starting to have adopted as well is we run Chrome in multiple processes, right? So what that means is that you go to one web page and it's in one process. You go to another web page in a separate process. And so if one is malicious, it'll crash and the other one won't crash. Now, we did that in 2008. Everyone, I think, expects this now, right? Even if a page just uses too much memory, it'll just take down that page and the other ones stay alive. It sounds kind of silly today, but most applications aren't developed like that, right? And so what that means is you need to kind of refactor your entire code base to do inter-process communication to be able to do that, right? It's actually not that hard, but it does take a while, and it has huge payoffs though, right? So it's the same thing, if you're decoding random inputs from the internet, put it in a different process. You can sandbox it using the OS's sandbox capabilities, and that's really, really powerful. So what do I mean by that? Well, when you start a process, you can ask most operating systems today, this process, I don't really trust it. So if it does a syscall to do something kind of weird, just let me know. Or if it does a syscall to create a file, just kill it. I don't want it to be able to create files. I'm talking with it with one pipe and that's it. So the operating system won't accept the application doing any weird syscalls that you tell it not to accept. Now that's very platform specific, right? So again, there are a lot of kind of different solutions for sandboxing processes. First thing, put code you don't trust inside its own process, reduce its privileges, but you have to figure out how to do that for the particular platform you're running on, right? So for example, on Linux, you may want to use seccomp BPF, which allows you to just say, hey, well, if I see this syscall, kill the process or whatever. So it's a pretty simple trick, but it works really, really well. Now, another thing that browsers have to do is we put hard-coded limits on stuff, right? So it's actually possible to have a PNG file, I think, that is 1 kilobyte or something smaller that ends up decoding to something that's 1 gigabyte, I think, or multiple gigabytes. And that's great from an image standards point of view, right? You just said, hey, I had this thing, just repeat this pixel a bajillion times, and it's really big. Now, from a browser's perspective, if you gave me this tiny thing that I downloaded from the web and then you inflate it to a huge amount of memory, that's kind of bad, right? In that case, it'll just make the browser crash. It's a bit unfortunate, but there are a lot of other things where having hard-coded limits is really useful. For example, if you ask Chrome to run a portable executable that's bigger than 32 megs or something like that, it'll just refuse to run it, or 64 megs or something like that. First, it's pretty silly to run a really big application like that. It's not that silly, but it's useful to have hard-coded applications because what we've seen is that attackers often try to send us a bunch of code, and then they'll jump randomly at one place, and that may start their execution chain. All right, so pretty often attackers just spam you because they have an attack that works statistically well, but it requires a huge amount of data to work out. So it's really useful to have hard-coded limits in your application. Another thing that we do is we use exponential backoff quite a bit, right? So in a browser, if you start a web page and say the web page runs Flash and Flash crashes, right? So Flash runs in a separate process, lower capabilities and everything. Say Flash crashes. Okay, that happens. You're on YouTube, the video doesn't play. Okay, just reload, right? If it happens again, then we start kind of looking and doing exponential backoff because as a browser vendor, we're thinking, hey, there's probably a bug in Flash and someone's trying to screw with us, right? So we do exponential backoff, and what usually happens is the attacker has, again, an attack that statistically works, say, 1% of the time, right? So if, say, we have 1 billion users and it works 1% of the time, that's a lot of users, right? Now, if we start doing exponential backoff on that, that reduces the number of times this attack will work quite a bit, right? So it's pretty interesting to do kind of these types of things. And what we do is we look at a domain and we say, well, we don't really trust that domain anymore because it keeps crashing our stuff. So like maybe we'll try running its thing 5 minutes later or something like that. And then one thing that browsers do in general is you can opt in to send us statistics, right? And when I say send us statistics, what that means is we literally have like an array of counters of like how many times you've clicked on the screen, or how many times Flash has started, or more interestingly, how many times Flash has crashed, right? Or how many times, you know, how many nodes we've rendered in a web page or something like that. And so those statistics, if you opt into it, and a very small proportion of Chrome users do, but they're really, really useful as a signal for us to see when there's kind of a wide-scale attack going on. And now that's a place where you as an application developer probably have a leg up on browser vendors, because usually applications, you kind of get to choose what runs, right? And so what that means is basically you should have monitoring on your application, right? If you're afraid of getting hacked and you can't monitor what's going on, you're probably getting hacked, right? So I highly recommend having pretty strong monitoring in your application. And just a parallel to what Google does, you know, when you go to google.com, we log basically, you know, the number of queries that we get and the number of queries per second that we can render and stuff like that. What that allows us to do is that when there's a bug in our code base and our number of queries that we answer goes down, we notice, right? We notice regressions in our QPS quality. But if our servers start going down as well, we also notice that, and we can address those issues, right? So it's really useful as, you know, kind of a cloud company or something like that, to see when things are going bad. And so Chrome does a small amount of that, but you know, we do respect people's privacy, so we ask them before doing it, even though it's literally just a counter that increments. And then one critical thing that Chrome kind of started, but that's, you know, basically every browser does now, is we update about every 6 weeks. And that's really, really useful, right? It used to be that like you updated your browser when you wanted to, and maybe it was hackable, maybe it wasn't. Updating frequently has been really, really good for security. And then one thing that we can do as Google is we can also crawl the web and try to see if there are websites that try to download malicious executables or something like that. And then Chrome has kind of a side list of websites that it thinks may be malicious. And if you try to go there, we'll tell you, hey, this looks malicious. Are you sure you want to go there? Right, so there's kind of this neat integration, and Firefox uses the same list of signals that we use for that. So we kind of just publish a list of websites we think are bad, and they can use it too. So again, this is a subset of what Chrome does. I try to concentrate on what tools you can use, but we do a lot of other things with, especially with networking, with privacy, with UI and stuff like that, because most of the time, the weakest link isn't the technology in our case, it's really the users, right? We'll ask the user, are you sure you want to go to this website? And they'll say, yes, it said there was a picture of a cat in there. I want to see the cat, right? So pretty often we have to try to help the user understand what's going on, right? The users aren't stupid, they just don't really know how technology works, right? And so it's really, really hard for us to explain that to them in a way that allows them to make the right choice for them. Now, one thing I haven't really mentioned is, well, I kind of have, right? So I talked about OS sandboxing, and we're just, you know, Chrome is just a user-level application. We run just like any other application. We don't control the kernel. Now, if we did control the kernel, say with Chrome OS or say with Android, we could do a lot of interesting things, right? So for your applications, you probably do control the kernel, and so you can do a lot of interesting stuff that we can't do. For example, you can use virtualization, right? Chrome can't just like start a hypervisor and run in there, right? Whereas you can do that. Now, there's trade-offs to that. There's a cost, but you know, it's kind of interesting. At the same time, Chrome is a beautiful attack surface for injection, right? So what happens is user installs Chrome, user installs another application, the other application installs itself inside of Chrome. It just says, hey, when Chrome gets started, load my DLL too, right? And then the application will just like do random things inside web pages, track your stuff like that. So we also have to deal with that type of stuff. Right, so detecting that is actually quite hard, and because you know it's running inside the user's machines, and it's another type of a problem that we have to deal with that you may not have to deal with as well. But that, you know, we can measure, like we can see this affects our stability. Our Chrome crashes quite a bit because of malicious applications or extensions that are kind of clueless or stuff like that. Now, we have a bunch of things that we do, basically security in depth, right? Attackers love attacking us. The reference here is this is Pinkie Pie, right? Pinkie Pie is a famous hacker that hacked Chrome a few years ago. So it's funny. Come on. So Chrome has this thing called the vulnerability reward program, and actually it applies to huge parts of Google as well. And we basically like pay people a lot of money to hack us. And I think the rewards go from like $2,000 or $3,000 if you find like some small thing that we can fix easily, but you don't really know how to reproduce it or something like that, to tens of thousands of dollars. To, I think the biggest reward we have outstanding right now is $150K. I'm not sure. It's on the website. If you Google like vulnerability reward program, if you manage to hack one of these Chromebooks permanently, you get $150K. So go ahead, try it. So pretty often, we do all these defenses, and it sounds great. Attackers are really, really smart is the problem. And Chrome developers are fairly smart. We're kind of dumb sometimes. We make silly mistakes. And so pretty often, all they need is like one small thing to basically own the application. And that's kind of unfortunate. And so there are really silly bugs that happen sometimes. Like, for example, on OS X, I don't know if it's still the case, but until recently, in C++, the virtual function tables were writable from the application, right? And so that's not cool, right? So and like if I use the LVM on Linux or something like that, my vtables get loaded to memory. It's read-only memory, and all it is I'm like, hey, I'm going to do a virtual call now. It looks, oh, hey, what's your type? Okay, so let me take this function. This is your version of the virtual function. And I'm going to go and execute it, right? So, whereas an attacker says, hey, I found a way to write into the vtable. Let me do that. Right? And obviously, it writes, the attacker writes whatever pointer he wants into the vtable, and then he gets our execute arbitrary code. And usually what attackers do is they start calc.exe on your machine. So that's cool. Now, attackers do a bunch of other things. For example, I think there was a Microsoft presentation earlier yesterday that had a great example of type confusion. So it was kind of an HTML page where you gave it like some canvas thing that was some object, and then you kind of traversed that through the type hierarchy. And it happened that the browser implementation got kind of confused. It was like, oh, I have a canvas, and then this is a PNG, and then maybe this is like some other bytes somewhere like this. And it started interpreting the bytes that I thought were canvas as like a pony or something like that, and did something completely silly and allowed the attacker to like completely own the machine, right? And that happens fairly frequently because types are actually pretty hard, right? Now, there are other kind of interesting classes of bugs. If you go in the slides that I'll upload, I have links to these. And we publish all the bugs after a short while, after we've kind of secured all of our users. There was an interesting bug last year, or this year at pwn'd. It's called a time of check, time of use bug. And so what happens is on the GPU, what you did is you said, hey, I have a buffer. Here's the buffer, and it's this big. And could you just like put it on the screen? And what the attacker did instead is he started 2 threads. And he has the GPU, hey, I have a buffer. Here's the buffer. Here's the size. Could you put it on the screen? And he did that from 2 threads. It was clever, though. He put 2 different sizes for the buffers. So that was very confusing to the GPU code because the GPU code is used to running JavaScript. JavaScript doesn't really have threads, or use not to. And so the GPU code would look and say, hey, okay, I'll put that on the screen, and it did a few things, and said, what's the size of the buffer again? Right, okay, so I'll put that on the screen. And so because the code was given the size twice, the size was only checked once. There was a race condition in the code, but because it was attacker controlled, that allowed the attacker to do very malicious things. Now, the person who reported that bug got a lot of money for it. That was great. And then there was the obvious kind of use after free bugs or something like that. So if you go look at the Chromium bug tracker, we kind of publish all these things. They're kind of horrendous, kind of interesting. Sometimes they're very difficult to exploit. I think 2 years ago, the exploit chain was like 9 different exploits that we used back to back to back to finally break out of Chrome, right? Because as I said, we have a sandbox within a sandbox within a sandbox. You have to kind of break out of all those things. But eventually, a clever attacker ends up doing it. But so far, I've talked about like C level application code inside the browser. I haven't really talked about JavaScript. And JavaScript is a wonderful attack surface. It's beautiful. right? So JavaScript's a dynamic programming language. I talked about type confusion. Talk about type confusion. Have you ever written JavaScript? Right? It's really confusing, but it's great. Like I'm not hating on JavaScript. It's a great language. It's a glue thing that allows you to modify things, but it's pretty confusing sometimes. Now, it's confusing for the writer. Imagine for the compiler how confusing it is. And the reason it's really confusing is types are really, really bad for speed. In JavaScript, a variable could be a string, could be an integer, it could be anything. Right? So when I say a plus b, am I trying to concatenate? Am I trying to like add numbers together? I don't know. Right? So what JavaScript ends up doing, the biggest win for speed in dynamic programming languages is type tracing. So what you do is you execute the code, you record the types that happen, and then you kind of hard code it inside of your JIT. You JIT stuff that says, this is probably an integer. Just check at some point in time it's an integer. If it's not an integer, just like, we'll recompile the code again, right? So what the compiler does is it looks at the code and it dynamically regenerates code as the code executes. Now, that happens to be really, really fast for code that behaves well. It happens to be really, really slow if like, you have a function that's just called add and it takes in strings and integers and whatever. It happens to work really, really badly if you happen to exploit a bug. Right? So compilers have bugs pretty often. People find those bugs and exploit them, which gets us to kind of interesting things. There are papers about how you can secure JITs. Basically, one example of attacking a JIT is I'll write JavaScript code, and I'll have, JavaScript only has doubles. I'll write like a list of doubles. Right? So I'll just have like, 3.14 and other stuff like that, a bunch of them. And at some point, I'll figure out how to execute arbitrary code, and I'll jump into those doubles as if they were x86 code and just execute it. Right? That's really clever, but it works really, really well. It works very reliably unless you're randomizing the JavaScript code that you generate. And the same thing occurs with things like compilers want to be really, really fast to be able to generate code more rapidly, and so they map the executable pages as read and write also. It's a really bad idea. If ever you're writing a JIT, don't make your pages read, write, execute. Because you know what that means? It means that the code that you're executing can be modified at runtime. That's a horrible idea, but it happens to be really, really fast. And there's a bunch of other types of attacks that I'll refer to you in the slides. For example, return-oriented programming. You can create NOP sleds, try to get to the code that you created, and even without knowing what the code looks like, you can try to poke at the code a bit and figure out what it's doing to kind of create a Turing machine to attack the browser or something like that. So there's all these attacks that you can do, and the browsers are really screwed. And now, I've been talking about C++, this is the C++ conference, I haven't really talked about C++ that you can write. So what's interesting is I said, JavaScript is a dynamic programming language. Surely we can do better with C++. Yes, we can. So what's great is when you compile C++ code, it compiles to one static binary, right? So it means that there's no like type changing all the time and stuff like that. So why is it not silly to take your code from the internet and running inside a user's browser? It's not silly because it's actually quite simpler than running JavaScript, right? I can take the same backend for an engine because it knows how to generate x86 code or something like that. But it's just a one-time compilation, right? So I can apply a bunch of tricks that I detailed to compile that code into the browser, but do it much more securely, right? Because I don't have all these dynamic things going on. So it's actually quite simpler than compiling JavaScript code. One example of doing that is what native client did. Native client had this is the native client validator. If you pass this validation, believe me, your code cannot hack the user. Now, there's a paper about it, wonderful, and it's been in production in Chrome since I think 2009. Now, if you look at Chrome's release notes as well as any other browser, there are usually a few exploits fixed per release. Care to guess how many exploits were fixed in native client in production ever? Zero. Wonderful guess, sir. So as far as we know, NACL's never been exploited. Now, there were some near misses. It was used to attack APIs. For example, the time of check, time of use bug that I talked about earlier was through NACL, because NACL can be used to run threads, and threads can talk to the GPU and stuff like that. So it's used as a stepping stone to attack the browser. As far as I know, it's never been used in production. We never had to patch it, which is great because we don't have pagers, and so I don't have to like wake up at night and go and fix something. Now, our security team happens to do that pretty often for the rest of the browser. Now, unfortunately, as you'll remember, NACL only works inside of Chrome, and that's really, really sad. Now, why is that? There's a bunch of reasons. I can talk about it after the talk, but we are trying to fix it. We have WebAssembly that's incoming, and then we have other things like Sub-Zero. So we created this separate compiler for a portable native client. And the idea is we're doing all these kind of interesting modifications. I put kind of some links on how we do that inside the slides if you want to go peruse that a bit more. But if ever you're writing a compiler, or if you want to use a compiler, and you want to make things pretty secure, right? If you're JITting code that you don't trust, all these things you kind of want to do. Now what's great is we're also trying to do that within LLVM. So if you were to use LLVM as a JIT, you could have all of this goodness of like, hey, I'm just consuming code, I don't know what it is, I want it to run fast, but I don't really want to trust it. Right? So all these kind of mitigations are implemented inside of Sub-Zero, and we're trying to put them inside of LLVM. It takes a bit longer. Now, WebAssembly is incoming. What's interesting is WebAssembly, again, it's kind of based on the same JIT compiler as JavaScript is, but it has a side entry into it. So the attack surface is different, but it's much smaller. It needs to do less optimizations because the code's been optimized on your machine, the developer's machine, not on the user's machine. And instead of just having these objects that float around in a garbage collector that moves them around all the time, we kind of just give it a very fixed heap inside of the address space. And so it's kind of easy to check that it doesn't leave that heap, right? You can't confuse the objects because they're inside this very narrow address range. And so effectively, we've gone back to Harvard architectures, if you know what these are. So the code is very separate from all of the data that you're executing, right? You as an attacker would not have any insight to what the code is doing. All you see is the data that you put in there. That does mean that indirect calls are somewhat slower, but in general, it means that if your application has C++ undefined behavior, that undefined behavior turns into fairly limited non-determinism, right? So if you, for example, use atomics and they're racy, you'll see one value or the other, but you can't like just go and launch the missiles or something like that by doing this. So hopefully I've convinced you that C++ on the web is a good idea, that you may want to use it, and that security is something that works within browsers, and maybe you got like one or two things out of this, including using the sanitizer. So thank you. Any questions?
So I'm curious, with WebAssembly, is it possible for C++ to interact with JavaScript?
With WebAssembly, you can interact with JavaScript, yes. JavaScript does expect post message most of the time, but WebAssembly, at least the first version, will run inside the same process, and you can actually do calls directly to JavaScript, and JavaScript can call directly to it. Now, what's a bit horrendous is JavaScript is based on a kind of timer model, right? So you can't do that infinitely, right? So JavaScript usually expects you to kind of yield back and kind of go out of main and then back in all the time. And so it means you can't just do arbitrary complex things and like recurse into yourself and stuff like that. But you can do some amount of talking to JavaScript. Yeah. Yep.
Oh, I was wondering just about the WebAssembly connection to, or the WebAssembly connection to like a networking stack. How is that working?
So right now you can't talk to the networking stack,
Okay.
right? Because there is no web API for that. Once there is a web API for that, you will be able to talk to the networking stack. It will be limited because we don't want application developers to be able to talk to just any random web page.
Okay.
Right? Yes.
I guess more from an architectural standpoint of code, as a C++ developer, since this sort of like we're cross-compiling our what looks to us regular ISO C++ code, we just tell LLVM init the WebAssembly backend, that gets uploaded to the internets somewhere, and then on the hosts, when they're running it in their browser, there's a JIT that's compiling the WebAssembly down to what would be native machine code.
Yes, correct. So what you said basically is that on your machine, you're using LLVM to compile, or any other compiler, right? But you're using it to generate something that's a portable executable that's not specifically x86 or ARM or MIPS or something like that. And on the user's machine, you look at what architecture is there, and yes, it kind of just-in-time compiles that entire application into that specific ISA. Now, that does mean that you're making some form of a performance trade-off, right? So if you have very, very tight lock-free algorithms, they'll probably still work pretty well, actually. One of the reasons that we're working pretty closely with the C++ Standards Committee is to make sure that atomics work well. For example, it's wonderful that is lock-free is a runtime query and not a const-expr. So in a supercomputer, you're kind of like, well, I know exactly the machine I'm going to run on. I'd like to have is lock-free be a const-expr. And wonderful news that may be in C++ 17. But in general, is lock-free will remain a runtime thing that you like, as a start of your application, you're like, oh, well, I have this like lock-free linked list. If it's lock-free, I'll use a lock-free linked list. If it's not lock-free, it's not a lock-free linked list. I'll just slap a mutex around it and do that, right? So you can kind of dispatch your code differently. So you are making trade-offs in performance, but most of the time it's actually quite fast. And we've measured the performance, for example, on native client. The geomean in x86-32 for running a subset of spec2k, the non-Fortran subset of it, is about 10% overhead. Right now, geomean means that some applications are like 80%, some of them are some bigger gain.
I guess then the follow-up question, is there like a noticeable difference between, say, using this processor running C++ on the web versus going back to, say, JavaScript, which, I know Google's port immense resources in getting BB8, up and really, really fast JavaScript on the web.
Yeah, so why aren't we making just making JavaScript faster and basically compiling to ASM.js? So you kind of hit a limit with what you can do compiling ASM.js. ASM.js is a great feat of engineering. It's beautiful and ugly at the same time, how the type system kind of works out. If you don't know how it works out, I recommend going to read it because it's quite cute, right? It's a dynamic type system that happens to statically be provable as types. But you kind of hit a limit. If you go to the design repository that we have for WebAssembly, we have reasons for why we want to move away from ASM.js. And coincidentally, the main authors of ASM.js are the part of the main authors of WebAssembly, right? So it's not like we're inventing this thing to kill ASM.js. We're actually trying to do something different. Now, the other reason to do WebAssembly and not JavaScript is that I'm not sure I want threads inside of JavaScript. Right? Like JavaScript is a fine language the way it is. There are interesting things that you can add, like arrow function and other stuff like that. Maybe operator overloading. I'm not sure about that one. But WebAssembly doesn't care about operator overloading. But if we wanted to support threads inside of WebAssembly, we'd have to add it to JavaScript. And it's not clear that it's a good idea. There is actually a proposal to do that. I think it's going to be presented at the JavaScript Standards Committee soon. And you may think like, well, okay, well, like SIMD is in the same bucket, right? Like it'd be really silly to add SIMD to JavaScript. Bad news for you. That was standardized 2 hours ago. So JavaScript is currently, the Standards Committee for JavaScript is currently recommending that browsers that want to ship SIMD inside of JavaScript do so. Now, it's not that bad. SIMD is a great performance feature. I'm a bit sad that JavaScript beat C++ to the punch there, but there's a lot of features that will get standardized for WebAssembly that you may not want for JavaScript, and then we have the nice shortcut into the VM where we can do a lot of clever tricks instead of saying, oh, well, maybe there's an object and it changes type at runtime and stuff like that. Yep.
Are there any plans in the works to support dynamic linking?
Oh, do we want to do dynamic linking? Yes, please. Go to design repo. There's a thing that talks about this. There's a big issue about it. It will not be in the first version because it's really, really hard. We want to be able to do versioning kind of seamlessly so that like we say we think you should do versioning this way. We built a toolchain that does it. Maybe we're wrong. You can write a different toolchain that does it differently. But yes, we want to be able to do dynamic linking. Yes.
Could somebody build a runtime on top of WebAssembly that executes JavaScript in threads, but using a different model than the default one you get when JavaScript loaded to JavaScript?
So could someone execute a runtime, create a runtime that runs inside of WebAssembly that runs JavaScript and uses threads to do something different? Have you been on Twitter recently? Because I had exactly this exchange with Brendan Eich. Brendan Eich created JavaScript. So yes, you could, once we have all the features required for it in Java, in WebAssembly. Right? It may not be that fast, kind of related to dynamic linking. We want to be able to do dynamic code generation. Now, the way this would present itself is as a completely different backend. For example, I don't know if you're familiar with QEMU. QEMU is a way to, like, you kind of can emulate different types of architectures, right? So I can run an ARM binary inside of my x86 machine. That's done through a fairly silly JIT. It's pretty straightforward. If QEMU wanted to support WebAssembly's JIT system, it could. It would just have to target a different architecture. Exactly the same thing would be the case for V8, right? So in the ideal world, 5 years from now, WebAssembly can, like, you can take V8, compile it to WebAssembly. WebAssembly knows about the V8 knows about the WebAssembly backend, JITs JavaScript code into WebAssembly that V8 then optimizes to actual x86 that then executes on your machine. That's a binary translator that gets translated to an internal ISA that runs inside a hypervisor that's actually running inside of QEMU. So you could do that, yes. Yes, sir.
For the randomization, can you actually use like the C++ standard randomized functions and randomized the randomized functions? Can you use those inside of containers or?
Can we use the C++ standard randomization functions for randomization? Yes, we can. Now, unfortunately, when we do randomization of binaries, we do want the randomization to be reproducible. That sounds completely stupid. Let me explain why. As a developer, I'm going to change my JIT. So I'm going to change the compiler, and it's going to start crashing. If it starts crashing and I had a random number generator in there, I won't be able to reproduce the crash. So I want to be able to provide a very deterministic seed, which the C++ random number generators can do. Now, they can do that if you're careful. For example, if you use random shuffle, good luck to you, sir. That will not do what you want. If you use the stud distribution class, I think it's called, good luck to you, sir. That will not do what you want either, because that's the way it's specified isn't actually deterministic. So if I change the C++ standard library that I'm using, it'll give me a statistically similar distribution, but with a different list of random numbers, even though I seeded it exactly the same way. So yes, we can use C++, but we have to be careful.
Okay.
Yes.
It's just kind of like one follow-up because I also do work in embedded. So, you know, it's sort of like you get your C++ code, you compile it straight to the machine code, but you don't have access to a lot of libraries because it's just, you know, at that point, machine code, so you don't have a lot of library access. So I guess the question becomes is if you start doing this on the web, are you going to run into the same thing where it's sort of like we'd like to use, say, the STL or some random boost library, but at that point, suddenly the JIT or the instrumentation in the browsers actually needs to have some kind of, I guess you could say, hosted environment for those libraries to bring them in.
Right, so your question is from an embedded perspective, you don't really get to use all the cool shiny toys that all the C++ developers get. Will that be the same case in the browser? Yes and no. So as you saw, I had Emacs running. I can actually run GIMP on this, right? So I can run X11 and GTK and GIMP and everything, right? So let your imagination run wild a bit. If you look at how a C++ standards library is implemented, most of it is actually quite straightforward-ish C++ code. Very little of it is non-portable, right? So the part that you're actually worried about is when you start calling the kernel most of the time. And that's where things get really tricky. And so if I'm using stud algorithm or something like that, no problem, this all works. If I'm using stud future, yeah, maybe it's a bit trickier if I use stud thread. If I start using thread local storage, that's a bit different. You know, there's some portability aspects there. If I use atomics, obviously that's very tricky to do portably. It's possible because C++ exposes it in an interesting way. If I start doing I/O, that's pretty tricky, right? Especially as I showed you, if I start touching the file system, I'm not touching the actual file system, right? It has to run inside its own domain. So it's a tough question to answer. It really depends on the API you're trying to use. But most of the C++ standards library just works. A very small subset does not. libc is a different question. libc is actually quite harder to support portably. Now, interestingly enough, the team I work on has experience porting not one, not two, but 3 libcs to run on the web. So why would we do that? Because we hate ourselves. Now, luckily enough, we do have the current maintainer of glibc working on our team. So if we have questions about running C libraries, we can ask him. He has about 30 years of experience running glibc. So it's actually quite difficult, and it takes domain experts to really efficiently target different operating systems really well and provide an abstraction layer that makes that portable and kind of trivial for developers to just use, right? Like from your point of view, developer don't give a damn, right? Like it should just work, right? And that's what we're trying to do, right? So the goal is really the tool chain that we ship for WebAssembly, it just works. Yeah.
What's the anticipated timeline for WebAssembly?
Wonderful question. Next question. You can look at the GitHub repo. There is no statement of a timeline.
Are there any sort of big, obvious things that you'd like to run in at the moment that you can't?
Are there things that we'd like to run on the web that we can't right now? The main things we're trying to aim at are really high performance things right now, right? So games are really it. Code that already exists, like I showed you, is another thing that we'd like to run. But really, it's like build it and they will come type of thing, where we just kind of give you the power to run most of C++ really efficiently, and we hope that just whatever comes to that, right? So what's interesting is, we have a ginormous install base, so it should attract people to our platform. But at the same time, from a user's perspective, I think the web security model is really attractive, right? So what we're trying to do is we're trying to get people to use the web. And then ideally, the users win, the developers win. So to a certain degree, I don't really care what you run inside browsers. And actually, I don't want to know what's on the internet, honestly. It'd just be cool if everything kind of worked. Right, so if you want to run finance stuff in the browser, more power to you. Please don't start mining Bitcoin using our user's machine.
They do that already, no?
They probably do that already, and we may have mitigations against that.
Just switching gears a little bit, you mentioned a lot of things that developers can do that Chrome does to its application security.
Yep.
Sandboxing, auto updates, reporting. Is there any way for developers to leverage Chrome's an open source project? I'm thinking between Mojo or Chrome Embedded Framework, maybe more recommendations of how you can use our.
Well, so I think the easiest part of Chrome technology to use inside your application is the sandboxing side of things. Obviously, V8's pretty straightforward to use. We use it within Google to JIT random stuff that we care about being fast. And Node.js, for example, uses V8 to make things fast. And some of V8's security layers use some of Node.js uses V8 security layers to secure itself. So I think really the sandboxing with specific parts and the JavaScript engine are probably the simplest things to use. Yeah.
Could you expect that you get kind of robust debugging tools, like say through the browser of WebAssembly?
Next question. Stop asking me difficult questions. No, so your question is about debugging. Do we expect it to work well? In the initial version, not that well. If you look at what browsers support today, they have a thing called line maps or something like that, where so a lot of language cross-compiled to JavaScript, right? It's not just C++, it's also GWT, so Java and whatever other Ruby and other things. The way it works right now is you can ship a line map thing, so that's like compiling with -g line maps or something, and that's about it. So you get kind of printf and you get symbol names that maybe are kind of the same if you haven't mangled your JavaScript. That's cool for debugging, right? Eventually we want to do something much more powerful, but it's easier to start with that and then kind of move forward. All right, well, thank you.